Humanity, ever since it first cast its gaze upon the night sky, has posed a fundamental question. Where does all this end? Does a final wall exist, a cosmic boundary beyond which neither space nor time extends? Or are we merely a grain of sand in an infinite boundless ocean of reality, one that has neither beginning nor end in space? Today, armed with data from telescopes that peer 13.8 billion years into the past, we know that the universe is expanding. Galaxies, like dots on the surface of an inflating balloon, are racing away from one another. But this very analogy, intended to simplify, immediately creates a logical trap. If the balloon is inflating, it must be inflating into something, into some external space. So, into what is our universe expanding? The answer from modern cosmology is both profoundly elegant and counterintuitive. The universe is not expanding into anything. Space itself is expanding. This was not an explosion of matter into a void. It was an explosion of space-time itself. The Big Bang did not happen at a single point. It happened everywhere simultaneously, at every point that now exists, including the one you occupy. Therefore, the question, what lies beyond the edge, lacks physical meaning in the classical sense. There is no outside, as outside presupposes the existence of space. The universe is the definition of all the space that exists. But this does not mean the question of finiteness is resolved. It simply transitions from the geographical plane to the geometrical and topological. Is the volume of the universe finite? And is our cosmological journey doomed to be forever constrained by a horizon we can never peer beyond? Part 1. The Geometry of Fate. The answer to the question of the universe's finiteness is inextricably linked to its fundamental geometry. Einstein's general theory of relativity teaches us that matter and energy warp spacetime. Depending on the total density of matter and energy, including dark matter and dark energy, the universe can have one of three possible shapes. The first option is a closed universe. This is a space with positive curvature, analogous in 3 dimensions to the surface of a sphere. This universe is finite in volume, but boundless. Just as you can walk on the surface of the Earth forever and never reach an edge, yet the planet's surface area is finite, so too in a closed universe, a hypothetical spaceship flying in a straight line would eventually return to its starting point. In this model, gravity is strong enough to one day halt the expansion and initiate a big crunch. The second option is an open universe. This is a space with negative curvature, resembling the shape of a saddle. In this geometry, parallel lines eventually diverge. This universe is infinite in both volume and extent. There is not enough gravity to stop its expansion, and it is fated to expand forever. The third option, and the one that aligns most precisely with our current observations, is a flat universe, a space with zero curvature. This is the geometry we learn in school, Euclidean geometry, where parallel lines always remain parallel, and the sum of angles in a triangle equals 180 degrees. Data from space missions like WMAP and Planck, which mapped the cosmic microwave background, have shown our universe to be flat with a margin of error of less than 1%. A flat universe, in its simplest interpretation, is infinite. This means that space stretches on forever in all directions, filled with an infinite number of galaxies, stars, and perhaps lives. Part 2. Solving the horizon problem. But how did the universe become so astonishingly flat and uniform? When we look at the cosmic microwave background, the echo of the Big Bang coming to us from all directions, we see that it has a practically identical temperature everywhere, about 2.725 Kelvin. This phenomenon is known as the horizon problem. Imagine two opposite patches of the sky. The light from them has only just reached us after 13.8 billion years. This means they are separated by nearly 28 billion light-years from each other. In the standard Big Bang model, these two regions could never have been in causal contact. Information, even at the speed of light, could not have passed between them to agree on the same temperature. So, why are they identical? The answer is provided by the theory of cosmological inflation. According to this model, in the very first fraction of a second, approximately from 10 to the minus 36 to 10 to the minus 32 seconds after the Big Bang, the universe underwent a phase of exponential, faster-than-light expansion. It increased in size by a factor of at least 10 to the 26th. This process took a minuscule, causally connected, uniform patch of space and stretched it to colossal, astronomical scales. This is precisely why our universe appears flat to us, much like the surface of a gigantic balloon seems perfectly flat to an ant. Inflation not only solved the horizon problem, it also explained where the fluctuations that seeded the galaxies came from. They were quantum fluctuations, stretched to macroscopic sizes. Inflation implies that the universe we see is just a minuscule fraction of a much, much larger, or infinite, structure which is predominantly uniform, far beyond our vision.
To be continued in Part 2, coming this Friday. Subscribe and turn on the bell so you don't miss it.